glad you're with us on First Principles Daily, episode 25. It's June 30th, 2026. Let's run the magic wand number and the idiot index on today's subject. Before containers, dock handling often cost more than the sea voyage itself. Afterward, the entire system converged on the steel and fuel floor. In the 1950s, a typical break bulk freighter spent 3 weeks or more tied to the pier. Gangs of longshoremen moved cargo crate by crate and pallet by pallet. A single ship might require 200 workers and hundreds of separate lifts just to empty and refill its holds. Malcolm McLean refused to treat that handling step as an unavoidable fact of life. Instead, he asked what the physical minimum would be if every piece of cargo arrived already inside a standardized, mechanically handled box. For decades, the maritime industry had optimized the ship and the sea leg while leaving the dock largely untouched. Ship designers lengthened hulls, improved engines, and refined hull forms because those variables sat inside their traditional domain. The cost and duration of cargo handling were accepted as someone else's problem. Ports therefore remained collections of finger piers, warehouses, and rail sidings sized for loose crates, barrels, and sacks. Labor contracts, union work rules, and the physical layout of the waterfront all reinforced the assumption that each item had to be touched multiple times by hand. Under that regime, the finished cost of moving a ton of general cargo through a port routinely exceeded the cost of carrying the same ton across an ocean. The industry's mental model treated the ship as the expensive asset and the dock as a necessary but secondary delay. No one had redrawn the boundary around the entire transport chain. The default approach began with the ship itself. Naval architects focused on hydrodynamic efficiency and cargo hold volume, because those parameters had been the levers of progress for generations of sail and steam vessels. Once the hull was designed, operators simply filled the open 'tween decks with whatever mix of bales, drums, and cases arrived at the pier. They relied on gangs to stow and secure each piece with rope, dunnage, and plywood. That process required repeated lifts from dock to deck, then from deck to lower hold, each lift demanding separate rigging and supervision. Because the cargo units varied in shape and weight, no single crane cycle could serve more than a handful of items. Damage claims from shifting loads or weather exposure remained routine. Everyone inside the system therefore treated high handling expense as an immutable property of moving mixed freight rather than a consequence of the chosen transfer unit. McLean began with the observation that the dominant term in the cost stack was not steel, fuel, or hull maintenance, but repeated human handling at the interface between modes. A rough magic wand estimate for the physical floor of ocean freight therefore starts with the commodity price of the steel in the hull and containers, plus the fuel energy required to push the loaded ship through the water. Everything else is process overhead. In the pre-container era, that overhead produced an idiot index for port handling easily in the range of 10 to 20 times the underlying material and energy cost. The redesign therefore had to attack handling directly by making the box itself the transfer unit. The first concrete move was to fix the external dimensions and corner fittings so that the same box could be lifted by a single crane. The box could then be placed on a truck chassis or stacked inside a ship without rehandling its contents. That single decision eliminated the need for individual slings, nets, and dunnage for each crate. A rough arithmetic check illustrates the leverage. If a conventional break bulk lift cycle handled perhaps 2 tons per sling and required 4 minutes of coordinated labor, a container lift moving 20 tons in 90 seconds removed roughly an order of magnitude of touch labor per ton. This held even before accounting for reduced damage and weather exposure. Next, the ship itself was re-specified. Cellular holds replaced open 'tween decks so containers could be stacked and locked without additional lashing by hand. The port followed. Instead of finger piers and warehouses, new facilities needed only wide aprons, rail-mounted gantry cranes, and straddle carriers. Truck chassis were standardized to accept the same twist-lock corner castings. Each of these changes removed a layer of labor and time. Each also required the adjacent systems to change in lockstep, or the box would simply create new bottlenecks elsewhere. The standards war of the late 1960s and early 1970s was the visible cost of achieving that network compatibility. Once the dimensions and fittings were frozen, crane cycles dropped from many minutes per lift to roughly 90 seconds. A ship that once spent 20 days in port could turn around in 2. One obvious objection is that locking the dimensions too early might strand future improvements in box size or strength. The counter-argument, visible in the record, is that any later change would have multiplied the cost of every crane, ship cell guide, and chassis already built to the original specification. The network effect therefore rewarded an early, stable interface even if individual boxes later incorporated stronger corner castings or lighter steel alloys. Another objection concerns cargo that cannot fill a full box. The redesign addressed this by allowing the box to serve as a temporary warehouse on wheels or rail. Partial loads still avoided repeated manual handling inside the terminal. Well-documented studies of the period show port handling costs per ton falling by roughly an order of magnitude within a decade of widespread adoption. The new idiot index for the handling step moved much closer to the steel and fuel floor. It never reached unity because cranes, fuel, and the containers themselves still require fabrication and maintenance. The remaining gap lives in terminal real estate, regulatory approvals for new facilities, and the capital cost of the cranes and ships sized for the standardized system. Those limits are physical and institutional rather than conceptual. No further redesign of the box itself can remove them without altering land use rules or crane technology. The residual idiot index therefore reflects the cost of the heavy lifting equipment and the land it occupies, not the original labor of piece-by-piece transfer. When one narrow activity, such as manual piece-by-piece transfer, dominates total cost, the only move that matters is to make that activity disappear by redefining the unit of transfer. The second principle is that a standard strong enough to coordinate cranes, ships, trucks, and ports must be frozen early. Any later change multiplies the cost of every adjacent asset already built around it. What would be the first measurable signal that another industry has begun treating its own handling or interface step the same way? That's a wrap on today's first principles breakdown. The ideas travel further when you pass them on. Send this to a fellow builder. I'm Patrick in Vancouver. See you tomorrow. And if you'd rather watch than listen, find us on YouTube at Nerra Network. Links in the show notes. This episode used AI voice synthesis of my voice. Editorial selection and analysis are my own.